Good morning, everybody. Welcome to my presentation. My name is Yinjun Chen. I'm now a professor at the University of Winnipeg. The talk I'm going to present today is about a polynomial time algorithm to solve the so-called two-merge sort problem. This problem proves to be NP-complete. Here is the outline of this talk. First, the motivation of this work. For this, I show you what is satisfiability problem, as well as what is two-merge sort problem. Both of them are NP-complete. Then I present our algorithm to solve the two-merge sort problem in polynomial time. For this, the following concepts and techniques will be discussed in greater detail, such as p-graphs, p-star graphs, and tree-like graphs. Then we search the tree-like graphs will generate is a layered representation. Then by using the layered representation of a tree-like graph, we can solve the two-merge sort problem efficiently. Then I analyze the time complexity of this algorithm. Finally, I conclude with a brief summary of this talk. Here is the motivation of this work. For this, I show you what is satisfiability problem. For this problem, we are given a logical formula in the conjunctive normal form like this, where each Ci is a clause which contains a set of letters as shown here. The problem is to find a truth assignment for each variable such that each Ci evaluates to true. This problem is NP-complete. The maximum satisfiability problem is an optimization version of satisfiability that seeks a truth assignment to maximize the number of satisfied clauses. This problem proves to be NP-hard. The two-merge sort problem is a simplified version of the merge sort problem with each Ci containing at most 2 letters. Even though this problem is a simplified version of the merge sort problem, this problem is still NP-complete. The main idea of our algorithm is to transform the two-merge sort problem to another problem which can be solved in polynomial time. For this, we consider a logical formula in the conjunctive normal form, something like this, with each Ci containing at most 2 letters. Then we define another logic formula, but in the disjunctive normal form like this. Well, each di1 is equal to ci1 and xi, and each di2 is equal to ci2 and minus xi. Here, xi is a newly introduced variable. Then we can prove that formula C has least n star satisfied clauses if and only if formula D has at least n star satisfied conjunctions. Then we have a new problem to find a truth assignment that maximizes the number of satisfied conjunctions in a logical formula like this, where each di is a conjunction. If we can solve the above problem in polynomial time, then we can also solve the two must sort problem in polynomial time. As an example, let's have a look at this simple logical formula, but in the disjunctive normal form. If we let C1 equal to 1, C2 equal to 0, C3 equal to 0, C4 equal to 1, C5 equal to 1, and C6 equal to 1, then we can find a set of disjunctives, a set of disjunctions, D1, D3, D5. Each of them is satisfied. In fact, they are a maximum subset of satisfied conjunctions. To find such a maximum subset of satisfied conjunctions, we just introduce a new notation, something like this. It is equal to Cj or minus Cj. Then this notation always evaluates to true. Our purpose is to use this notation to represent any missing variable in a conjunction. Then, in this way, we can change the above formula D to a new logical formula, but the value of this new logical formula is the same as the previous one. But doing this enables us to represent each conjunction as a variable sequence like this. Okay. But with each negative leaders being removed, now we are able to compute the appearance frequencies of variables in variable sequences like this. Then we can impose a global ordering of variables such that the most frequent variables appears first. Then for the above variable sequences, we can impose a global ordering of variables like this, where variable C5 appears first. It is because the appearance frequency of this variable is the highest. Then we can sort each variable sequence according to this global ordering of variables. For example, we can sort this variable sequence to be a sorted sequence like this, where a start symbol and the ending symbol are used for technique convenience. Now we are able to generate a graph structure called P-graph for each conjunction. For example, for this conjunction, we can generate a P-graph like this. In this graph, we have a main path going through every variable in this conjunction. In addition, for each star notation appearing in the conjunction, we have a spine. For example, for this star notation, we have this spine. For this star notation, we have this spine, and for this star notation, we have this spine. We can also represent each spine by the subpath covered by it. For example, for this spine corresponding to this star notation, we can represent it by a subpath going through 3 nodes, V2, V3, V4. For each P graph, we can define another graph called P star graphs. For this, special attention should be paid to the overlapped spines. In this P graph, we have this spine overlapped with this one, and this spine is also overlapped with this one. But you should notice that this spine is connected to this spine, but they are not overlapped. Here we can see that the union of 2 overlapped spines make a new, bigger spine which covers 2 consecutive star notations. Then you can see that the overlapped spines exhibit some kind of transitivity. Then our purpose is to find transitive closure of all the overlapped spines. In this way, we can define P star graph as a main path plus the transitive closure of all the overlapped spines of the corresponding P graph. This graph, P star graph, is very important because in this graph, each path represents a truth assignment and which the corresponding conjunction evaluates to true. For example, if we just go from this node, start node, then go to this node, this node, and this node, then going along this edge to the end node, we just get a truth assignment and which the corresponding conjunction evaluates to true. But we can go along another path. We just get another truth assignment and which the corresponding conjunction also evaluates to true. For example, if we just go starting from this node, then this node, and then this node, then going along this spine to this node, then this spine go to the end node. We just get another truth assignment and which the corresponding conjunction evaluates to true. Now, what we want is to merge all the B star graphs together to generate a tree-like graph. But in the first step, we'll generate a tree over all the main paths in the P star graphs constructed for all the conjunctions. By tree, we just mean a tree in which each path is just the main path in the corresponding P star graph. For example, this path is just the main path of the P star graph constructed for the first conjunction. And this path, it is another main path in the P star graph constructed for the conjunction D4. And this path is just the main path in the P star graph constructed for the conjunction D6. Then we just add all the transitive closure of the overlapped spines to this tree structure to create a tree-like graph. Here, special attention should be paid to the number associated with the spine, which is used to indicate what P star graph this spine belongs. For example, the number 4 associated with this spine is used to indicate night. This spine belongs to the P-star graph constructed for conjunction D4. And the numbers 2, 3, 4 are used to indicate this spine belongs to 3 P-star graphs constructed for 3 conjunctions T2, D2, D3, and D4 respectively. Then I'll search this toy-like graph bottom up. First, we just recognize all the leaf nodes to make up the first label. It is the first label. Then we just try to find all the parents of the nodes at this label to get the second label. All the nodes at this label will be categorized into different groups. Such that in a group we have all those nodes with the same labels. For example, these 3 nodes have the same labels, also the same variable names. C3, then all the 3 nodes will be put in the same group. These 2 nodes are also labeled with the same variable name, C2, then these 2 nodes will be put in one group. All the remaining nodes are differently labeled, then all these nodes will not be continually explored. In the next step, the nodes, the parent of the nodes in each group will be explored. We just get another label. Also, the nodes at this level will be categorized into different groups. We just repeat this process until we meet a level such that all the nodes at this level are differently labeled. Then the whole working process stops. This layout representation is very useful because by using this layout representation, we can find the answer to our problem very efficiently. For this purpose, we just recognize all those nodes in this graph, which does not have a parent. We just call such a node a root. For example, this node is a root, and this node is also a root, and this node is another root. Each root recognizes a subgraph like this, which contains all the nodes. Each of them is reachable from the root. Each rooted graph identifies a set of conjunctions which can be satisfied by the same truth assignment. For example, the rooted graph, subgraph, contains these 5 nodes, represent a set of 2 conjunctions, D2 and D4, which can be represented by a same truth assignment. To know this, we just have a look at this slide. This slide just shows that the subset which contains 2 conjunctions, D2 and D4, can be represented by a truth assignment represented by this set of variables. That is, any variable in this set will take a value equal to 1, while all the other variables which do not appear in this set will take value equal to 0. All these variables are the variables appearing in the path from the root of the tree until this node, plus any path in this rooted subtree. You can see another example. In this example, we have a rooted graph which contains 4 nodes. This rooted subgraph identify a set of conjunctions D1, D3, D5, which can be satisfied by a truth assignment represented by this set of variables. This working process can be greatly improved is because in this process, a lot of loads will be repeatedly accessed. For example, this part of the graph is completely identical to this part of the graph. Then any nodes in this graph should not be explored. In this way, we can get a polynomial time algorithm to solve the 2-mask sort problem. In summary, in this talk, we have presented an algorithm, polynomial time algorithm, to solve the 2-mask sort problem. For this, a lot of interesting and important concepts are discussed in great detail. There are p-graphs, p-star graphs, as well as triangle graphs named by such. Triangle graph we can generate is layered representation. By using this layered representation, we can find the solution to the 2-mask sort problem in polynomial time. Because the 2-mask sort problem is NP complete, then our algorithm is in fact a proof of P equal to NP. Okay, that is all for this talk. Thank you for your attention.